Hello and welcome to this code review. We are going to discuss and review the design and the implementation of a very complex UI component that you see right now on your screens. So we have a stack of cards and you can drag these cards around, you can throw them into the air, and you can throw multiple cards into the air and all of them land at the back of the stack and then animate to their correct respective position. Now, I was challenged to implement this UI component using classical Android views, and it turned out that it's really challenging but also really interesting task. So there is a lot we can learn from the implementation of this component, and therefore I decided to record this video to capture all these lessons for you. Now, just to calibrate expectations, we are not going to discuss that much user interface and animation stuff, because it turned out that, just drawing this component and animating all these cars was maybe 25% of the complexity. The most complex part of this component comes from the state management. So we have all these cars that each of them has its own state, and we need to manage the state of the cars and interdependencies between these states. So that's the most interesting aspect of this component. That's what I'm going to discuss the most in this video. And therefore, even if you don't like UI, you will still find a lot of interesting stuff right here. Okay, without further ado, let's just get to the source code and review the implementation. The implementation of this component consists of two custom Android views. So we have card view, which implements just one single card, and then we have stacked cards view, which implements the entire element within which the cards are animating. So card view by itself is a very simple component. So all we do here is just drawing one single card. So in onDraw, we draw this round rectangle, that's the background, and then we draw a circle and two more round rectangles to represent these text dummies. And inside onSizeChange method, we just compute various sizes that need to be drawn on the screen. And the reason why we do that inside onSizeChange and not inside onDraw, because onDraw can be called multiple times, and therefore it's a bad practice to perform any computations here. So whatever you can extract from onDraw to some other method, or just compute whenever this class is initiated, that will be the best approach, because onDraw should execute really quickly. And in this case, we don't perform any computations inside onDraw, and therefore the implementation of this card view is really optimized for performance, even though it's not a complex view at all. All right, so that's the card view, and the most of the complexity, all the complexity of this component resides inside stacked cards view class. So that's what we're going to discuss the most in this video. Okay, let me just hide my emulator and let's get to it. First of all, just like with card view, we perform all kinds of computations inside onSizeChange method to initialize, top card width, top card height, top card translation X, top card translation Y, card shift, that's the shift between cars, etc. So basically, we compute all of that in order to make it account for the new size if the size changes, but also not to perform these computations too often. And then I call to initCars method, which initializes all the cars. But please notice that I use this post. Why is that? Well, because for some reason, if I would call just initCars right here inside onSizeChange, then the cars will not be initialized properly. So I use post to postpone the initialization to the next frame. Basically, I allow this custom view, stacked cars view, to initialize, and only then I call to this initCars method, which just removes all the views from this custom view and then loops through number of cars in the stack, initializes each card, and then adds the cars to this list and adds the view associated with the card to this custom view, and then calls to this update translation X. So a bit of stuff here. What's important to understand here is the notion of a card. So initCard returns this myCard class. And myCard class is not a custom view, but myCard class contains a custom view. So you see, it takes card view as the constructor argument, but it by itself is not a view. Why is that? Well, because myCard represents the state of the card on the screen. And the view, the custom view that we use here, this card view, is just one of its properties. It's not the entire myCard. And of course, I could take all this code that I have inside my card and theoretically put it inside card view, but then it would make card view very specifically targeted at this animation. And I didn't want to do that. I wanted to keep this card view very simple and reusable. So currently there's nothing in this card view that says that it should be used just in this specific animation. But my card class is actually optimized, implemented for this specific use case. So this way, again, I keep card view UI element reusable and simple, and all the complexity of state management is shared between stacked cards view, custom view, and my card inner class. Okay, so my card is a general class that represents cards on the screen and has card view as one of its properties. Now, when we discuss my card, it has a state. So my card has a state, and the state can be either of these states. So card can be settled. This means that the card completed all the animations and settled in its final position. It can be dragged. This is the state when you click on the card and drag it around. It can animate snap back. That's when you release the card without throwing it, so it should just get back to its original position. You can the card can be animated, throw animation. That's of course when you throw the card, and the card can be in this state, animate position shift. And that's the state. Let me show you that. Please notice that whenever I throw a card, all other cards animate their position shift. So basically the green card will come to the foreground and the yellow card will also go forward in order to free the position for the red card to land in. So that's the state, animate position shift, when the card just animates its position from its current position to the final resting position. All right, so that's the state that my card has. And it has also state animator. That's of course because some of the states involve animation, and therefore we want to have this animator as the property of my card in order to, for example, cancel it. So we have this cancel state animation method, and whenever cancel state animation is called, we remove all listeners from the state animator and then cancel the animation. We will discuss when and why we do that a little bit later. And then we have just some properties. First drag is a property that we use in order to identify the first time the user drags the card. We will need to rotate the card a little bit. Let me show you that. So when I just take this card, it's rotated a little bit, and in order to perform this animation only when I just grab the card, I use this first drag property. And some properties related to last action and last action down row X and row Y, translation X, translation Y, and last action down event X. So this is just me capturing various aspects of the last user's interaction in order to compute various properties related to the animation and the position, rotation, and scaling of these cards on the screen. That's my card. And my card handles motion event by itself. So basically it has this handle motion event method. We receive motion event, and then depending on the type of the motion event, we invoke one of these methods. Where this handle motion event is called? Well, it's called from onTouch event of stacked cards view. And here, please notice that whenever onTouch event of this parent view stacked cards view is called, there is this touch target card property that should be initialized already, and therefore we just route this interaction to this touch target card. Where this property is being initialized? Where is being initialized? Right here inside onIntercept touch event method. Now this method is kind of tricky and nuanced because most of the time you wouldn't use it. What this method does is basically letting the Android framework know whether this view, in this case stacked cards view, intercepts this event and whether the next events in the sequence should be delivered to onTouch event of this specific view. So how do we know whether this stacked cards view should intercept the events? Well, this is a tricky part here. And to understand the trickiness of this interaction, I would like to go back and review the following commit. Refactoring touch handling. Okay, so let's take these two and review the difference between these two commits. And the caption, the title of this commit is refactoring from view interactions to translation Z. So before that, see here, I used card view and I set onTouch listener on each individual card view. So basically each card handled its own touch events. And this was really simple implementation. And then inside update all cards, I removed the card view and added it back while accounting for the position of this card view inside the stack of cards. Why did I have to remove view and add it back at some specific position? Well, that's just because how Android handles touch events. Android routes touch events first to the first view that was added to this parent view. And in this case, the parent is of course stacked cards view. So whenever we touch the screen, Android computes which view should handle the touch. And if there are multiple views at the same position, then the first added view will handle the touch event. Now, I have to manage which view is the first one. Basically, I have to manage the ordering between these views, because when I throw the card and it goes to the background, there are times when the cards can overlap. Cards in the stack overlap, right? Let's see here. This green card overlaps the blue card. And when I touch here, Android should route the touch event to the green card and not to the blue one. And that's what I achieved using this specific code. And basically, not just touch events, but also the ordering of the cards. So if I would change the ordering of the blue and the green card here inside this code, then the blue card will be drawn over the green one. And that's of course incorrect. So this code managed this aspect. And then turned out that this approach, while it's simple, doesn't work that well. And the problem is that when I remove this card, well, it worked, everything was fine. But when I remove the card and add it back, when I remove the card view, sorry, and add it back, then what happens is that if I actually drag the card at that time, then the drag event, basically the touch event sequence, is completed and the card is released. And while not the end of the world, that made this element less interactive, less well designed in my opinion. And therefore I had to implement another approach. And another approach that I used, you see this right hand side, is to use translation Z. So with translation Z, update all cards method, this same method that removed the views and added them back in the respective position. Now all it does is just updates the translation Z property of the card view. So card views are not removed in this method anymore. Instead, we just update the translation Z property. So this handles the ordering of the cards on the screen. This handles the elevation of the card. However, there's a problem. In Android, when we used views, basically the form was the first view that we added was the first one rendered on the screen, but also the first one to receive the touch event. And this actually worked quite well. But when we use translation Z, it doesn't actually change the ordering of the touch event handling. And therefore still, the first view that we added to this parent view, to stacked cards view, would handle the touch event. And obviously that's not very good, because the translation Z property changes. So some of the views go to the background, others come to the foreground, but they remain in the same position added in the parent view. So the background view could potentially start handling interactions that you intend basically to drag, the foreground card, but instead you will drag the background card. And therefore, when I switched to translation Z, I also had to override onIntercept touch event and onTouch event methods. And what I do here is basically deciding which card should handle this interaction. How do I do that? I take basically the X and Y components of this motion event, and they pass them into this isPointInView method. And isPointInView looks at the coordinates of the view and accounts for the potential of the view being rotated. That's why we have this invert matrix and map points calls. And after we determine whether the point is in the view, we basically set this touch target card to hold a reference to the touched card. And of course, we must loop through all these cards in the stack in order to find the touch target card that has the highest translation Z value. That's the topmost card, the foreground card in our stack. And when we find this foreground card that should intercept the touch event, we return true, right? So if we have touch target card, then we will return true, meaning that next interactions with these elements should be routed to onTouch event method of this parent view, which in turn will route these interactions to the selected card. Otherwise, if touch target card is null, it means that, we clicked somewhere where there is no card, and therefore we don't need to intercept all the next touch events, and therefore we just return false from this method, and the next touch events will not be routed to this stacked cards view. So that's why I have this relatively complex method here, because I could use actually the ordering of views inside the parent, but then I sometimes just lost the interaction. So if I would drag a card, it will just snap back, because if ordering change would happen when I drag the view, it will just lose the drag event and the view would return to its position. So I had to refactor it for better user experience, and actually it wasn't that bad. I was afraid that it would be very bad, but actually it wasn't that bad. It took maybe 40 minutes to perform this refactoring. Alright, so all in all, we intercept touch events and we find the card that should handle these touch events going forward. And if we find this card, then when further touch events happen, we just route these events to that selected card that handles these touch events depending on the type of the event. So whenever action down happens, we just, initialize some properties related to action down and transition to drag state. Okay, so this is very interesting. And so now we get into state management, which is the most complex part about this component. Okay, when I touch this card, right, you see that one of the sides of the card is being elevated. How does it work? Well, we handle touch event and transition to dragged state. And this two-state method implements a state machine basically. So it takes into account the current state and checks the next state and then decides what to do. So if the current state is settled and the next state is dragged, then we call to this animate drag rotation method. And as you see, this method, animations methods, are relatively straightforward, relatively simple compared to other stuff that we have inside this stacked cards view. And that's why I always claimed, that rotations, animations, implementing UI, that's not something difficult. Just several lines of code. So we have this value animator that runs from 0 to 1. And whenever the value inside this animator is updated, we just change the rotation of this view, start the animation, and that's it. We have this first drag flag in order to make sure that we perform this action only on the first animation, and all the rest of stuff is just initializing some boundary conditions and computing the actual rotation, point rotation, depending on the fraction of the animation that passed since the beginning of this animation. Very simple, very straightforward logic to rotate this card. So that's not what's difficult, what's challenging inside this complex element. Okay, so now you can see that from the settled state, okay, this is the settled state when the card is in its final resting place, we can go to either settled or dragged, that's the one we saw right now, or we can go into animate position shift method. How can we go into animate position shift? Well, very simple. I take this card and I throw it, right? And all other cards on the screen are now settled. But once I throw this card, it will start changing its position in the stack. And so other cards will need to change their position as well. And that's when the card transitions from settled to animate position shift. Let's see where's the logic that basically sends the card to animate position shift. Here's this method, transfer to position in stack and then new stack index. What we do here inside this method, well, we first of all compare and make sure that we don't need to do anything if the new stack index is the current stack index. And then the transfer looks as the following. If the state is settled, so if the card is in its final resting place, then we need to go into animate position shift. But it also might happen that the card is in dragged state. And that's very interesting state. So for example, I can throw this card and then instantly grab, for example, the blue card. And what I want to achieve is that while green card transitions to the back of the stack, the blue card, what I wanted to do is to animate its scale, depending on which index it transitions to. So let me just throw the yellow, okay, and then red. But I'll throw the blue and grab the yellow, and you see that the yellow grew in size while I was dragging it, right? Once again, I'll throw the yellow, I'll grab the red, and you will notice that the red card changes its scale. It becomes larger while I'm dragging it around. So throw, grab, and it becomes larger. So when I bring it back, it's actually in the same size that it should be. So this transition from dragged state back into the drag state is a very interesting corner case. I just wanted to make sure, that whenever you take the card and you drag it around, it changes the animation. And by the way, it wasn't that important because when I release the card, it animates back into the position and it could animate the scale while it's being animated back into the position. But I really wanted to nail everything about this complex UI element. So I worked hard to make sure that the card animates its scale even if you drag it around while other cards change their index. Let's just go back and review the state machine. So that's what we can do from settle state. We can go to settle, in which case we just set to index position without any animation, If we go to dragged, we animate the rotation of the card a little bit. And if we go to position shift, then we cancel the state animation. Why should we cancel the animation? Well, actually, in this case, I don't think that I actually need to call this cancel state animation, but it's precaution. I want to make sure that whenever I start this animate to default position and scale, there is no other animation running, executing, and therefore I cancel this animation. And actually, when I think about it, I should probably also put this cancel state animation here as well. So that's just precaution. I don't want multiple animations to run concurrently, because then the result can be undeterministic. That's what happens when we in the settle state. What can happen if we in the dragged state? Well, from dragged state, we can transition back to dragged state. And again, that's the case when I drag the card and it changes position. So I throw this one, drag it, and it changes position while, sorry, not position, but it changes the index in its stack while I drag it. And therefore we transition from drag to drag. We cancel any state animation that can happen and just animate this card to its default scale. And default is computed related to its index in the stack. So get card scale for index, that's the method that computes the required scale. And of course, just like before, the animation takes just several lines of code. So there's nothing really that interesting here in reviewing the animations themselves. And so from drag state, we can go to dragged, and that's this edge case, or we can go to animate snap back. And that's of course when I drag the card and release it and it snaps back to its position. So we go to animate to default position and scale. And of course, okay, we can cancel the state animation. For some reason, I forgot to cancel the state animation in some places. I do hope that I don't introduce bugs right now, because all of that is quite nuanced. Well, actually, now that I said it, I think that I'm actually wrong. I think that initially I put this cancel as the first call inside this animate methods, but then it turned out that there is an edge condition, edge case, that just requires me to not change the scale. And maybe that's the edge case. So when I drag the card, it animates its rotation, right? But if at the same time it happens that the card changes its index, then I need to start this animate to default scale animation. And in that case, I don't actually want to cancel the rotation of the card. So maybe that was the edge case that made me remove this cancellation inside all of these animate methods and just put them here whenever it needed. Maybe I will just, after I reviewed this code, I will just revert back all these additions, because I don't actually think that it's safe to cancel all these animations. There was a reason why some of these state transitions involve cancellation of the animation and others don't. So all these edge cases of state management, of animation state management, they were really tricky to get it right. So I will just revert all of that. Okay. So from dragged, we can go to dragged, or to animate snap back, or to throw. And that's actually the most interesting, the most involved transition. When I drag the card and I can flip it, and then it throws and lands in the back. So first of all, we cancel any potential state transition, because for example, we can drag the card and I can throw it before it animates its rotation. And in that case, we just want to cancel the rotation. But this is the most complex animation inside this element. So let's just go over what's going on here. This is just initializing all kinds of stuff. This get boundary conditions returns this data structure, card boundary conditions, that contains just the initial conditions of this card at the time when this method was called. So these are just the various properties of the card when the method was called. And then we compute the stack index, the eventual stack index, because we always throw the card to the back. So that will be just number of cards in stack -1. And then we compute, the fraction for the back index and the y and x positions for the eventual index. And we also store the expected stack index at animation end. So that's very important. And that will actually be stack index back. Okay, so it's the same, basically the same value. And now it tells me that maybe I don't need this one, but I actually do want to keep it. And then rotation direction. So depending on where you grab this card from, it should rotate to either left or right, counterclockwise or clockwise. So if I grab it from the left, it rotates kind of clockwise, and if I grab it from the right, it rotates counterclockwise. This rotation direction property is what controls that, and the total rotation degree then is just some multiple of the full rotation. Then we have throw interpolator. That's the interpolator that we will use to compute the offset of this card. And I admit it's very dumb, very stupid interpolator. I just used linear interpolator. The value that this interpolator produces, I wanted to go from 0 to 1 and then from 1 back to 0. So that's throw interpolator. Frankly, not the best interpolator I could use here, but I didn't want to spend time on trying to implement anything better. And then again, we initialize the animator, set a duration, set linear interpolator by default for this animation, and just add the update listener. And this is the most complex update listener inside this entire class. First of all, we compute several fractions. We have the default fraction of the interpolator, and then we have fraction for translation and a different fraction for stack index change. So what happens here is that when you throw the card, other developers who tried to implement this animation, what they did was, you throw the card and the card gets its eventual index. But what I did here is something more involved, more interesting. The card basically translates between different indices while it's animating. So I throw it here and it translates from index 0 to index 1 to index 2 to index 3 during this animation. So, and this fraction actually affects the index transfer. Once we computed the fractions, we just animate the car. So basically we set scale x, scale y, translation x, translation y, and rotation on the car's view. And these are just, computations that compute various parameters, not something interesting. And then we compute the new stack index, the stack index that this card should have while animating. And if this new stack index is not equal to the current stack index, then we call to this transfer card to stack index. And this method transfer this card and then computes the new stack index for all other cars inside the stack and calls to this transfer to position in stack on each of the cars and updates the translation z of all the cars in the stack. So whenever any card transfers to another index, we just recompute indices for all other cars and make sure that the translation z of all cars match these indices, these new indices. Okay, so that's the most complex animation here. And as you see, it takes maybe 15 lines of code to implement. That's it. That's the animation, 15 lines of code. And then when the animation ends, we want to set the rotation to 0. And the reason why I set it's just a quick hack, because after I throw the card, it doesn't end in the rotation 0, it ends with rotation 360. So I just wanted to reset it to 0 for all future animations. And then, depending on the stack index, we need to transition to a new state. If the stack index, the current stack index of this card, is the expected stack index at animation end, and I remind you I set it here, so I decided that this card is expected to be at the back of the stack when the animation ends. So if the stack index, current stack index, is exactly at the back of the stack, then, well, we are settled. So now the card, red card, is now in this final resting position, and we transition to the state settled. But it might happen if I throw multiple cards that blue card landed at the back, but its stack index wasn't at the back of the card, because while blue card was thrown, I threw other cards, so the stack index of the blue card actually changed from the back of the stack to something else. And then blue card, when it lands, it actually needs to transition to its respective final resting position, and that's what you see here. If I throw two cards, then you will see that red card lands at the back and then transitions to the foreground. Now, this is one of the most crucial aspects of this animation, and other developers who tried to implement it actually got it wrong. What they did was much simpler solution. They just computed the index of this card and let it land at its final resting position. But what happens there, if you just compute the final position and let the card land in its final position, is that if I throw the yellow card and then I throw the green card, the yellow card, even though it was thrown and should have landed at the back, if it just changes the position and lands in its final resting position, then of course it will kind of change the destination while it's mid-flight. If you do this animation very quickly, if the duration of this animation is really short, maybe you will not notice the problem, but that's not how kind of physics behaves. When you throw something, it has a specific landing position and it can't change the landing position mid-flight. So that's why we need this if condition. If we landed and the stack index of this card is exactly at the back of the stack, then fine, we are settled. But if not, if the stack index changed because other cards were thrown into the air while this card was animating, then we actually need to animate the position shift and shift this card to its final resting position. Okay, so that's basically the most important, the most crucial, the most difficult part that took most of the time to implement. So we stopped here from drag to animation throw, and of course from animation snapback we can go to settle state, in which case we don't need to do anything, but from snapback we can also go back to the drag state, in which case we need to cancel the state animation and animate drag rotation and animate to default scale. Basically we can catch the cars when they are animating and then they should behave properly for us. Or after the card is snapped back, but it's not in its final resting position, so it should animate to its final resting position then. And then after the card is thrown, it can transition to the settled state, and that's of course this condition when the card lands at the back and that's its final resting place. Or it can transition to animate position shift in order to transition to its actual final position. And this is this case when we throw more than just one card. And from animate position shift, we can go to settled, and that's of course, okay, card reached its final position and everything is fine. Or we can go to drag. So for example, when the card animates, I can still catch it and drag around. So we need to make sure that this transition also supported. Or we can go from animate position shift again to animate position shift. And that's of course when we throw multiple cards and one of the cards is animating one index forward, but then while it's animating, I throw another card. So now after it reaches its previous final resting position, it needs to transition to its new final resting position. So that's this transition from animate position shift to animate position shift. And all in all, that's where most of the complexity of this UI element resides. This two-state method and state management, state interdependencies, different animations when some of them needs to be kind of started, when I should cancel the running animation, and in other cases I don't want to cancel the running animation, and various edge cases like snap back and then immediately position shift, even though it doesn't happen that often. Or for example, when the card is animating snapping back, but then I catch it and I start dragging it around. Or when the card is animating position shift, but again, I can just catch it and start dragging it around. That's the hard part of this element, and not implementing these cards, you're not drawing this rectangle and circles, and surely not just putting them into the stack. That's not what took most of the time. Most of the time was spent just debugging all these state transitions and making sure that I cover all these edge cases. And of course, there's this very interesting aspect that I wanted this animation to be physically realistic. So when I throw the card, I want it to land at the back, even though maybe I threw other cards, and then transition to the foreground only after they land at the back. It would be much simpler implementation if I would just, when I throw cards, I compute their eventual resting position and then let them land in that position right away instead of landing at the back and then transitioning to the foreground. But that wouldn't be very realistic, and this implementation is much better, even though it took a lot of time to get it right. And all in all, that's it. This concludes our code review. I really hope that you enjoyed spending time with me here and potentially learn something new for yourself that will help you in the future, whether you develop UI elements or not. Because as we said, most of the complexity of this UI component did not even come from UI or animations, but was related to managing state, to implementing this very tricky finite state machine. The last thing that I would like to ask you is, if you like this video, if you like my style, then check out my video courses. I created some of the most advanced Android development courses in the world, so you can find them if you go to my website /courses. And if you would like to learn some more advanced topics with me, that will be a great pleasure for me. I will be really happy to be your instructor. And with that, let me just thank you for spending time with me, for trusting me with your time, and I'll see you next time. Goodbye.